Bismillahirrahmanirrahim. Today we will discuss symmetry. You know that symmetry is basically it is a transformation under which an object remains invariant. It has different types we have different types of symmetries. Translation, reflection, rotation, and scaling. These are different types of symmetries. Translation, it is a symmetry in which invariance of a system of equation under any translation. That in this symmetry, every point of the object moves by the same distance without changing its shape. Like that, if you have a line y is equal to x, then a transformation y is equal to x plus 1. This will transform every point of that line through plus 1, and then you can see that its shape will not change. Before transformation it is a line, and after transformation it is the same line, only that we have added 1 in every point of that line. So this is called translation symmetry, that we are translating something. No, what is reflection? Reflection is basically the mirror image about any axis, about any line or plane. Like that, you know that y is equal to x square, parabola. This is symmetric about vertical axis, x-axis, and transformation for this symmetric is x to minus x, which we change x to minus and y to y. That y does not change, that we are reflecting that about y axis, that we are mirror image about y axis. And similarly, a plane can also act as mirror. Suppose that as we have xy plane, mirror image about xy plane, and mirror image about xy plane will be z will be minus z. That if we take the mirror image of every point above xy plane, then its mirror image will be downward, that we are reflecting every point above that xy plane. This is a reflection. And scaling is another type of symmetry. An object has scale symmetry if it does not change its shape when it is expanded or contracted. Suppose that you have a square and you contract or expand that square. If after contraction or expansion shape will not change, then we say that that square has scaling symmetry. Shape will not change, only size will be changed. Now rotation symmetry, if the object can be rotated about a fixed point without changing its overall shape, that we can rotate any object about any fixed point or about any line, and shape of that object is not changed, then we say that that particular object has rotational symmetry. Now we will have to discuss this symmetry in our continuum. Based on this symmetry, we will have different type of continuum. We know that our matrix C represents the properties of continuum. like we say that f is equal to kx in Hooke's law. K is basically the elastic constant, spring constant. In previous classes you say that is spring constant. Here we have 81 components of elasticity tensor, which represents the properties of elastic material. In general we have 21 independent components. They represent the properties of a continuum. Now we will see that depending on these symmetries, different types of continuum we will discuss, that which type of continuum has which type of symmetries. We will say that, and also we will see that continuum which has any symmetry, that how many components can be reduced with the help of that symmetry of the elasticity constant, elasticity matrix. Now matrix C represents the elastic properties of continuum if C is invariant. If C is invariant under any transformation, as we have said in the definition, it is a transformation under which an object remains invariant. If C is invariant under any transformation, under a transformation, that is C is equal to C dash, it is invariant. This is after transformation, this is before transformation. Then we say that particular continuum has symmetry, because the transformation does not change that C dash is equal to C. It means that transformation will act as symmetry for that particular continuum. Let us define different types of symmetries. Here we have definition like n-fold axis of symmetry. An axis such that a rotation of theta is equal to 2 pi by n about the axis leaves all the properties same, or if we rotate through this, the components of tensor that describe the material remain same. Now what is n-fold axis of symmetry? If you rotate, let us take an axis and you rotate about that axis with the angle 2 pi by n, then if the properties of tensor which represents the material does not change, then we say that material have this type of n-fold axis of symmetry, that we rotate about that axis with this angle. This is called n-fold axis of symmetry. Plane of symmetry, you can see that this is the transformation for the plane of symmetry, that if you have xy plane, then this would be the transformation for that plane of symmetry. And center of symmetry, reflection through origin, that if you have center of symmetry, then this type of transformation will be here, x y z minus x minus y minus z, like y is equal to minus x cube, y is equal to x cube. Sorry, we say that this is symmetric about the origin. This curve is symmetric about the origin, that we apply the transformation y to minus y and x to minus x. It does not change that equation. Y is equal to x cube remains y is equal to x cube after the application of that transformation. This is suppose that we have one example, that how we apply the symmetry to reduce the number of independent components of a tensor. Suppose that you have a plane of symmetry and we choose axis so that your x3 axis is normal to that plane, to that symmetric plane. It means that if x3 axis is normal to that symmetric plane, then that symmetric plane will be xy plane, because x3 is perpendicular to x1 x2 planes. Then for that symmetry, this transformation will be associated with that symmetry. X1 dash equals to x1, x2 dash equals to x2, and x3 dash equal to minus x3. That if you x1 and x2 plane, then x1 dash equal to x1 after and before, x2 dash equal to x2 after and before, and x3 dash equals to minus x3, because it is above the x1 x2 plane, so its mirror will be downward. That will be equal to minus time x3 dash equal to minus x3. So from here we can write the transformation matrix 1 0 0 0 1 0 and 0 0 minus 1. Now we will see that we have a second order tensor. Suppose epsilon. If this is second order tensor, so it will have 9 components. We will see that how this symmetry will reduce the number of independent components. We know that this is tensor, so we can write this transformation law. And due to symmetry, as we have symmetry, so it means that epsilon dash will be equal to epsilon, because we are supposing that there is symmetry. So due to symmetry, epsilon dash will be equal to epsilon. No, this is the transformation law. With the help of the transformation law, we discuss the components. Epsilon 1 1 dash will be equal to a p1 aq1 epsilon pq. And now on the right side you will have to open the summation on p and q, and we can see that all the components of transformation matrix are 0 except the diagonal. So here will be only 1 1. Other than 1 at the place of p and q, they will be 0. So a11 a1 epsilon 11, so epsilon 11 dash equal to epsilon 11, so no effect on epsilon 11. Let us check epsilon 12 dash. Epsilon 12 dash equals to this. So here will be 1, here will be 2, so it will be again epsilon 12 dash equal to 2, epsilon 12, no effect on epsilon 12. Similarly, there will be no effect on epsilon 21. Let us check epsilon dash 13. It will be equal to a p1 aq3 epsilon pq. So this would be a11 and this is a33. No, this is plus 1, this is minus 1. So epsilon dash 13 equals to minus epsilon 13. What does symmetry say? Symmetry say epsilon 13 dash equals to epsilon 13. This is from here. Epsilon 13 dash equals to epsilon 13. So you can write from these two equations epsilon 13 equals to epsilon minus 1 epsilon 13, so epsilon 13 equals to 0. So again see epsilon 31 will also be equal to 0. Let us check epsilon 23 will also give you 0. You can check. You can check from here. This is plus 1, this is minus epsilon dash 23 equals to minus epsilon 23, epsilon dash 23 equals to epsilon 23. This is from symmetry, and this is epsilon 23 equals to minus epsilon 23. So epsilon 23 equals 0. Similarly, epsilon 3 equals 0. So tensor will become this. These 4 are 0. So we have 5 independent components. So due to this symmetry, due to xy plane, due to symmetric plane xy, this tensor, epsilon tensor, will have 5 independent components. 4 are 0. So symmetry has reduced its independent components from 9 to 5. Now we will see that the effect of symmetry on the number of independent components of elasticity matrix. So we have different kind of continuum depending on the symmetries they have. Let us start from here, that we have basically two extreme cases of continuum. One is triclinic and the other one is isotropic. Why they are extreme? Extreme in the sense that this has maximum number of independent components and this has minimum number of independent components. That isotropic continuum has large number of symmetries and this has very small number of symmetries. So when a continuum has more symmetry, then its components will be reduced, and if a continuum has less number of symmetry, then its independent components will also be less. Independent components of matrix C. When we see that independent of components of the continuum, it means that we are saying the independent number of components of matrix C, elasticity matrix, which represents that continuum. First continuum is triclinic continuum. It is a continuum that possesses only center of symmetry. Now the symmetries for different kind of continuum is already defined in the literature, so we are not here to find the symmetry. We will use only those symmetry to check the number of independent components of matrix C for continuum. So triclinic has only one symmetry, which is center of symmetry, and note that this center of symmetry will be present in all types of continua. And transformation for this center of symmetry is this: x dash is equal to minus x, y dash is equal to minus y, z dash is equal to minus z. That is about the origin, reflection through origin. So matrix transformation matrix is this. Now we will see that this symmetry, how many number of independent components can be reduced with the help of this symmetry for C matrix. We will have to check the number of independent components of matrix C, because for continuum we have matrix C, we have tensor, elasticity tensorCijkl C. So we will have to check the components of that elasticity tensor. And this tensor has symmetry, so C dash ijkl will be equal to Cijkl. That for the continuum we have elasticity tensor C, so due to this symmetry C dash will be equal to C. Now with the help of transformation law we can write this, and with the help of transformation matrix we can also write this. Why there is minus 1 power 4? We know that we have summation on right hand side PQRS on right, and Cijkl they are dummy, but we can see from the matrix that we have only non-zero components in the main diagonal. All other components of the transformation matrix A, I am talking about this, all of diagonal components are 0. So survival of the terms will only be possible in which we have diagonal elements A11, A12, A13, A11, A22 to A33. So there are 4. So minus 1, minus 1, minus 1, minus 1. So minus 1 power 4 Cijkl. PQRS will be ijkl. So it would be C dash ijkl Cijkl. So it means that there will be no effect on the components of C. So due to center of symmetry there will be no effect on see, no components will be reduced. Thus from here we can have a result that for a tensor of even order, if you have tensor of even order and if there is center of symmetry, then that center of symmetry will play no role for that even order tensor. Role in the sense that this symmetry will not reduce any independent components. Before and after the application of this symmetry, number of independent components will remain same, they will not change. But on the other hand, if you have odd order tensor and you are applying center of symmetry, then this center of symmetry will then due to this center of symmetry, all the components would be 0. That when we apply this symmetry, all the components will become 0. Suppose, for example, you have Lijk. These are the components of a third order tensor. So order of tensor is 3 odd. Now we have written transformation law for the component of third order tensor and use the transformation matrix. Then here will be -1 power 3, -1 and -1 power 3 Lijk. So L dash ijk will be equal to minus Lijk. So due to symmetry, L dash ijk equals to Lijk. So combining these two, we have Lijk equals 0 for all ijk. Here you can see that C dash ijkl equal to C ijkl, and here you can see that L dash ijk is equal to minus Lijk, and you can see that if you combine these two, Lijk will be equal to 0. So it is giving you that all components will become equal to 0. That if you have order tensor and you have center of symmetry, then due to center of symmetry, all elements will become 0. For even order, there is no effect. For odd order, all components will be 0. Now for triclinic material, as we know that for elasticity matrix C, for triclinic material there is no effect on C, so we can write elasticity matrix in this way. No components is 0. C11, C12, C13, C14, C15, C16, C11, C22, C23, C24, C25, C26, and like all other elements. So this would have 21 independent components. So for triclinic continuum, elasticity matrix would have 21 independent components, because triclinic continuum has only one symmetry, and that symmetry will not reduce the components of elasticity matrix. This was today's lecture. Thank you so much.